Hi, welcome to one more video on control systems. So in this video we will see transfer function of RC networks, in that poles, zeros, and we will see the MATLAB visualization of all these transfer functions for various RC networks. Just go through these basic slides. Okay, if you are ready, we will start. I will start with very basic circuits. Let me start with the first network, which we have already discussed in the previous sessions. We have actually derived it. Now in this particular video we will not derive it. We will use those transfer functions and then try to locate the poles and zeros, and if I add a resistor or capacitor at different position, how does the poles and zeros will come into the transfer function. We'll have a look at it. So let us consider a very basic RC network, which is a typical low pass filter. Now this is V0, this is Vin. If you say this is R1, C1, this is ground, we actually obtain the transfer function of this, which is nothing but V0 of S by Vin of S as equal to 1 over 1 plus S R1 C1. So from this we can know the pole position. So pole is at minus 1 over R1 C1. So I can certainly write the pole 0 representation of this. The pole comes out to be at minus 1 over R1 C1. So this is my S-plane representation of that pole. Suppose if you give the value of R1 as 1 kilo ohm and C1 as 1 microfarad. So we know that this pole position, which is minus 1 over R1 C1, it comes out to be minus 1k into 1 micro, which is minus 1 over 1 milli, which will be, of course, 1 milli means 10 power minus 3. So now this will be minus 1000. So we will have the pole at minus 1000. As you change the value of R1 C1, the pole position changes. Of course, this is a very simple implementation in MATLAB, so you can just have a look at it. So I have written the MATLAB code here. So this is, I am trying to enter the value of both R1 as well as C1. So this is my transfer function, where numerator is 1, denominator is coefficient of S is R1 C1, and of course coefficient of S0 is 1. So suppose if I run this now, if I run, it will ask for the value of R1. So R1, let me give it as 1000, and C1 it is asking for, let me give it as 1 e power minus 6. 1 e minus 6 is actually 1 microfarad. If I give these two values, if you carefully look at the poles and zeros of this, if you can see here, so this is a transfer function which is 1 by 0.001 s, which is exactly what we wrote here. Suppose if I show this, so substituting the value of R1 C1 as 1 micro and 1, so this comes out to be 1 plus S into 1 into 10 power minus 3, which is nothing but 1 over 1 plus 0.001 s. So that's what is the transfer function we saw there. So this is the transfer function what we saw it over there. Let me just see here. This is the transfer function, and of course we know the pole is at minus 1000. This is what is minus 1000, and of course we don't have any zeros. So if you see the zeros are not there. So 0 is an empty and pole is at minus 1000. Suppose if you change the value of R1 C1, that will naturally change. So now let me give a different value of now it is asking for the value of R1. So let me give it as some 100, again it will ask for the value of C. Let me give it as 1 e minus 6, which is 1 micro. So now that will result in, oh, I think we went to a different one, so let me stop this. Okay, this is for a different one. Let me just come here and then now, okay, this is for a different one. Okay, then now let me just come here and then run. So now it is asking, let me give it as now 1 e minus 6. This is that value. If you can see now, the pole is at minus 10,000. So pole is at minus, because I have reduced the value of R by 10 times, the pole has moved from minus 1000 to minus 10,000. So because the pole position is inversely proportional to the value of R. So we will go to the next transfer function and try to see what is the next network. So this is my first network. The second network, so I will consider a resistor R2 coming in series with this capacitor. So just have a look at it. Please write all these in your notebook so that it will be easy for you to recap what you are learned. Please write all these things in your notebook also. This will help you to recap the things whenever you want to. This is V0, Vin, again this is R1, C1, R2, grounded. We know the transfer function of the addition of a pole at addition of a resistance R2 in series with this capacitor will end up with a transfer function which we have already derived in the previous videos. So you can just recap them. If you pass, have a look at the entire derivation. This comes out to be 1 plus S R2 C1 divided by 1 plus S R1 plus R2 into C1. Now let me just demarcate both of them. Just put it in a different color. It's not visible. Now this is my second circuit. This indicates that there is a 0 also, there is a pole also. So now looking at this, 0 is at minus 1 over R2 C1. So there is a pole at minus 1 over R1 plus R2 into C1. Suppose if you take the values of R1, R2, let us take R1 is equal to R2 is equal to 1 kilo ohm and C1 is equal to 1 microfarad, which will give me a 0 at minus 1 over, of course this is 1k and 1 micro, so this is R2, so this is R2 C1, which is nothing but 1k into 1 micro, which happens to be 1 milli, which is, of course this is minus 1000. So there is a 0 at minus 1000. The pole is actually at R1 plus R2 into C1, which happens to be minus 1 over 2k into 1 micro, which happens to be minus 1 over 2 milli, which comes out to be minus 500. So the moment I add this pole here, a resistor here, this was my original position when there was no resistor. The moment I add this one, so this actually, now this is, the pole was actually here at minus R1 minus 1 over R1 C1. It actually comes to minus 1 over R1 plus R2 into C1. The 0 comes out at minus 1 over R2 C1. minus R2. This is a pole 0 position. This is my pole position, there is a 0 position. Actually, the impact of adding this resistor in series with this capacitor will bring the 0, which was not at all there in this. So actually the 0 is there at infinity. So 0 has been brought to a finite value, which is at depending on the value of R2 and C1. So this is what. So as per this example, so this is at minus 1000, this is at minus 500. So let us do the simulation of this. I already texted the code here. Just have a look at this. So do we have R1, R2 as well as C1? You can see this is the quotient of S in the numerator. This is the quotient of S power 0. You can see again it is in the denominator, the quotient of S is R1 plus R2 into C1, and this is 1. So I want to pass on the values of all R1, R2. So let me just run this now. When I run, I should be giving the values of all the 3 components. That is, let me run this again. It's asking for the value of R. So in the example we are given it as 1000 as the value of R1. C1 is 1 micro, 1e minus 6, and R2 is again 1000. This should result in a 0 at minus 1000, pole at minus 500. This you can see here. So of course this is the value of K, and you can see the pole is at minus 500 and the 0 is at minus 1000, which is exactly here. So this is the pole position, which is at minus 500. This is the 0 at minus 1000. So that's how we could able to verify the things what we saw in our design. So in our design we had the same positions. So this was at minus 500, this, but suppose if you change the values, it will go accordingly. You can just try for R1 is equal to maybe around 10k, and keep R1 as whatever 10 ohm. Find the value, put the value C1 as 0.1 microfarad. So you'll get whatever. So you can just test it for this. You can typically substitute those values, find out what is this, and they can verify it using the MATLAB also. So this is 10 micro, 10 into 0.1 micro. So you can just, I'll just leave it to you people, explore the poles and 0 position for different values of R1 and C1, and of course R1, R2. So let me just make this as R1, this is R2. Next we shall move on to next circuit, where we have, instead of adding a resistor in series with this capacitor, let me add a resistor in parallel to this. So let us see what happens. So now I have the third circuit, where I have it as, this is R1, this is again same original circuit what I had it, but I'll have R2 here. This is R2, this is V in, sorry, this is V in, R1, C1, R2, and this is V0. The transfer function of this comes out to be we're going to end up with the transfer function, so which will have its numerator as R2 by R1 plus R2. So that will be my transfer function, R2 by R1 plus R2 in the numerator. The denominator, it is 1 plus. So I will end up with S into R1 parallel R2 into C1. So this is a transfer function what we are going to have. Sorry, this is a transfer function. It is R2 by R1 plus R2 in the numerator. In the denominator it is 1 plus S into R1 parallel R2. Of course, when I say R1 parallel R2, so it is R1 R2 by R1 plus R2. So this is the value of that you need to substitute. Looking at this, the moment when I add a resistor in parallel to this C1, there is no 0 coming. So in the previous case, a 0 came to a finite value. Here there is no finite 0. So actually 0 is there at infinity. If you actually try to locate the poles and zeros, there are no zeros, but the pole is at minus 1 over R1 parallel R2 into C1. So this is the pole position. Now let us see what is, suppose if you have it as 1K, this was 1 micro. When this was not there, pole was at minus 1000. So minus 1000 without R2. There is no R2. The moment you put R2, so since we are keeping this as both as 1K, this is 1 micro. So this becomes 500 ohm. This becomes 500 ohm. This is 1 microfarad. Actually, the pole moves from minus 1000 to minus 2000. So the pole will go to, of course, now this is not the pole position. Pole is actually moved towards the left side. So this is now when R2 is there in the circuit along with R1 and C1. Actually, pole moves towards left side. So pole was here actually at minus 1 over R1 C1. Let us move to this. So let us have a look at the same circuit there. And one more thing you can see, this value is not actually adding any poles and zeros, but the DC gain of this will be different. So let me just tell you what is this DC gain is. The concept of DC gain is nothing but when the frequency of this is 0, what is the output? When the frequency of this is 0, what is the output? Since we know that we will be substituting S by j omega, so for DC gain, omega is equal to 0. So that's your angular frequency, which is nothing but 2 pi f. So when the frequency is DC, when it's a DC signal, frequency is 0. So you end up with this 2 pi f as 0. So this S becomes 0. Wherever S is there, substituted as 0. When you substitute this as 0, so does this become 1 by 1? So does the DC gain of this circuit is 1? DC gain of this circuit is 1. So come to the same here. What happens to the DC gain of this? Again, wherever S is there, substitute it as 0. So will you end up with 1 plus 0 by 1 plus 0? Is the DC gain again 1? So DC gain in this case it is 1. DC gain in this case it is 1. Let us see what happens. Let us verify whether the DC gains are 1 for the previous two circuits. So here you can see we have a statement called KDC, which is DC gain of the system, because system is representing the transfer function of that RC network. So DC gain for the first circuit should be 1. So you can just no, irrespective of the value of what, irrespective of the value of R1 C1, the DC gain is 1. Just a minute, let me just run this. Okay, now let me again run. Now it is asking for the value, so let me give it as this for the first circuit. C is 1 E minus 6, which is 1 micro, and if you see this, the DC gain is 1. So in the circuit we saw that, so when this is 1 micro and 1 kilo ohm, whether it is 1 micro, 10 micro, 0.01 micro or 1 pico, irrespective of the value of C, for DC gain this acts like an open circuit. So whatever is the input, that is the output, so gain is 1. So DC gain is 1 for this circuit. So that's what we saw there. Of course, you can just try with whatever value of RC you want. Just say it as 10 ohm and this as 1 nanofarad, 1 E minus 9. See, the DC gain is still 1. The DC gain is still 1. Of course, the pole positions will change as per according to the values. Now come to the second circuit and let us try to find out what is DC gain of this. So here we saw that DC gain of this is also 1. For the second circuit also the DC gain is 1, because you are substituting S as 0, which corresponds to j omega, because this S corresponds to j omega. When it's DC, omega is 0, so this becomes 0, so it is 1. Again, irrespective of the value of R1, R2, the DC gain is 1. So this is my circuit, this is my code for the second circuit. Let me run, give whatever value you wish. Of course, the pole 0 positions are certainly depending on this. However, the DC gain is independent of this. I am just giving some random value. So this is again some 100. Just have a look at the DC gain. So DC gain of this is 1. DC gain of this is 1. Now let us come to third circuit and try to find out the same DC gain. So let me again come to this. So in this transfer function, if I substitute the value of, now I want to find what is the DC gain of this. DC gain of this is, now again substituting S as 0, which corresponds to omega 0. When omega is 0, S becomes 0, which means that, is it not that R2 by R1 plus R2 divided by 1 plus 0 will have? Now, depending on the value of R1, R2, your DC gain depends. So, what is DC gain now? So, DC gain is R2 by R1 plus R2. Now, for this case, if I take it as 1K, so DC gain comes out to be 1K by 2K. This KK will go off, you will end up with a DC gain of 0.5. So, in this circuit, for the third circuit, if you just substitute the values of R1, R2, now the DC gain purely depends on the R1, R2. And of course, it's independent of capacitance. Now let me just come here and run. Okay, it's taking some time. Sometimes when servers, just a minute. We are here. Let me run this. Now let me just take it as 1000. This has 1 micro, 1 E minus 6. This is again 1000. So this should end up with the value of the DC gain as 0.5. You can see the DC gain is 0.5. Suppose if I just rerun this and give different values of R1, R2, let us see what happens. Okay, now let me give it as 1000 and let me give this as 1 E minus 6. Let us give the value of R2 as like maybe 100 ohm. So it's like 100 by 1100. So 100 by 1100 happens to be, let us see what is the value. So how much is 100 by 1000? You just verify, is it not 0.09? So it's like, okay, 1 by 1.1. 1 by 1.1, sorry, 0.1 by 1.1. So 0.1 by 1.1 happens to be this. So what you have now is 100 divided by 1100, so which happens to be 1 by 11. So 1 by 11 is this value. So this way we can able to find out the DC gain of different circuits. So DC gain typically corresponds to what is the output when the frequency is 0. When the frequency is 0. Okay, this is going fine. Now let us move on to next circuit. So these are the circuits which we already saw the transfer function. Now we are basically looking into where is the poles and zeros, what is the DC gain, how does a pole comes, 0 comes, okay, where does the position of, this is fourth circuit. So I have, this is my circuit now, this is C1, R1, this is V in, V0, this is reference. If you actually find the transfer function of this, so as you already know, V0 of S by V in of S is equal to S R1 C1 by 1 plus S R1 C1. From this, it is very clear that it has got, in S-plane representation, it has got a 0 at origin and it has got a pole at minus 1 over R1 C1. Again, if you take the value of R1 as 1 kilo ohm and C1 as 1 microfarad, so this comes out to be at minus 1000 and it's at origin. And if you substitute the values of, if you want to find the DC gain of this. So DC gain corresponds to omega 0, where S is equal to j omega. So then S also becomes 0. If you substitute that S as 0, does it become 0 plus 1 plus 0? Sorry, 0 by 1 plus 0. So this happens to be 0. So DC gain of this is 0. That is, if the frequency is 0, the output is also 0. Let me just go to my MATLAB code. Let me take the fourth circuit. If you carefully observe this, of course, for each and every circuit, please note the transfer functions. You can see this is the pole position, sorry, the 0 position, which is there at having a transfer function SRC by 1 plus SRC. You can see S power 0 term coefficient is 0 here from the numerator, but in the denominator it is 1. So this actually defines this transfer function. So once you are there, okay, let me just give values of let me just do this. Now let me give it as 1000, and this as 1 e minus 6 will give me, can you see the DC gain is 0? The DC gain is 0, and where is the of course this K is the root locus gain. So K is the root locus gain. Can you see the pole is at minus 1000, and can you see there is a 0 at origin? So this is the 0 position which is at origin, and this is the pole position at minus 1000. So this is the pole position. See here, this is pole position. And let us move on to next circuit, where we will have okay, let us have a circuit where, so we should have a resistor going in parallel to this. So in the next modification, the fifth circuit, what I have is, I'll have same C1 R1, but I'll put a resistor R2 in parallel to this. This is the resistor R2 coming in parallel to this. So I want to find what is V0. This is V in. So now the transfer function. So actually the 0 was there at origin. So when I actually put it over here, the moment I put this 0, the transfer function, which is V0 of S by V in of S, happens to be 1 plus S R2 C1 by 1 plus. So I will end up with 1 plus S into R1 parallel R2, and the DC gain of this also change, and in the numerator you'll also have something what is called as R1 by R1 plus R2. This is the transfer function what you won't have. Now let us give different values of R1 C1, and let us see, let me give R1 is equal to 1 kilo ohm, let me give R2 as 1 kilo ohm, and let me give C1 as, of course you can give whatever value that you wish. Now the moment I give this, so as per this, the 0 actually adding a resistor in parallel to this capacitor C1 will actually bring this 0 out of the origin to a finite value. So that is the what effect of adding a resistor in parallel to this C1. So now this actually comes from here to a position which is this. Now it is minus 1 over R2 C1, whereas this moves to minus 1 over R1 parallel R2 into C1. So this is the pole position, this is the 0 position. So according to this, this will be minus 1000, this will be minus 2000. So this has gone from moved to minus 2000, and this from origin it came out and put, it is now residing at minus 1000. You can check that. This is my fifth circuit. You can see I have the same R1 divided by R1 plus R2. This is the constant parameter. Can you see this is my R2, C1 and 1 as the coefficients of the numerator. Can you see the denominator coefficient, which is R1 parallel R2 and C1, and other coefficient is 1, S40 coefficient is 1. If I now substitute the values of, so now what is this value you are looking for? It will ask for the value of, okay, now let me give it as same 1000. This has 1 e minus 6, and give R2 as again 1000. Now the 0 will come to minus 1000, pole will go to minus 2000. Let us see the DC gain. DC gain happens to be half. DC gain happens to be half. So let me run this. See here, the DC gain is half. If you can see this, so this is my pole position minus 1000. You can see this is my, sorry, this is the 0 position at minus 1000. This is the pole position moved to minus 2000. So which is exactly evident here also in this. You can see this is my pole position, which is minus 2000. So this is a 0 position. If you change this R value, suppose if you make this R something like, okay, 100. If you make this 100 ohm and let this be 1 micro, and if it is 1K, so then this moves to 10,000, and this parallel combination of this is still more negative than minus 10,000. You can just have a look at it. So let me take this here, and of course you can see the DC gain also changes because R1, R2 have changed. The DC gain also changes. Maybe it is around 0.9 something. You can see now. Let me run here. Now I'll make this R1 as 1000. Let this be 1 micro, 1 e minus 6. Let me give R2 as 100. The pole actually, can you see the 0 has moved to minus 10,000? Can you see this is much more negative, minus 11,000, minus 11,000. See the value of DC gain. Can you see it has become 0.909? It's like, okay, 1K by okay, what is the DC gain? DC gain happens to be this much. What is the DC gain here? Can you see now this is 0. So what is DC gain of this? DC gain of this is 1 plus 0 divided by 1 plus 0, and you have this as R1 by R1 plus R2. So DC gain is actually R1 by R1 plus R2. So when the value of R1, R2 are both same 1K, so DC gain was half. So when R1 is equal to 1K and this is 1K plus 100, this comes out to be 0.909. So that's what is the gain you have, sorry, the DC gain that you have now, 0.909. Okay, we shall move on to next circuit. Let me see what the circuit I have listed for the next circuit. Okay, next one is, it is slightly different. Let us see what happens to this circuit. Now we were actually making this a resistor being added now in parallel with capacitor. Now let us add a resistor in series with this capacitor. Let us see what happens to them. So sixth one is, so let me have the resistor R2 in series with C1. So this is R1, C1, R2. We are actually adding a resistor here in series with this. Actually we had it parallel in the earlier case, now it is in series. If you actually derive the transfer function, all those things, you will end up with a transfer function which is equal to it is S R1 C1 divided by 1 plus S R1 plus R2 into C1. Carefully have a look at this and this transfer function. Can you see the pole position remains at origin? Can you see the the zero position remains at origin? The pole position has changed. Pole has actually moved towards the imagined axis, moved towards the right side. Meaning this remains at this point. This actually moves to right side. So this is the zero position, and this is your pole position, which is minus 1 over R1 plus R2 into C1. So actually when the denominator increases, when R1 plus R2 happens, it has to move towards the right side. So this is, of course, this comes out to be minus 500. If you take R1 is equal to R2 is equal to 1K and C1 is 1 microfarad. So with these values, this comes out to be at minus 500. This is at still origin. Where is this? Okay, let me go here. This is my sixth network what I have. See the transfer function. Can you see in the numerator you have the coefficient of S power 1 as R1 C1 and the coefficient of S power 0 is 0. And see this, the coefficient of S is R1 plus R2 into C1, whereas coefficient of S power 0 is 1. So upon doing this, now I will run this. When I run and give the value of R as 1000 and C as 1 micro and R2 also as 1000, I will end up with, can you see what happened to this? Oh, sorry, that is sixth one now. So this should not be there. Let me take out this. Okay, this is my, so this is my, where is the pole? Okay, you can see the, why this pole has, this is fine here. Just a minute. This is my SRC. Okay, pole zero should be at origin. Zero should be at origin, which is exactly this. Let me just take out this. Maybe at the background is something else is running. Let me just check it out. Now let me again run. So now, okay, there's a mismatch here. This is the sixth one. Let me run. Okay, it is 1000. 1e minus 6. This is again 1000. Now it's fine. You can see now the 0 is at origin. Pole is at minus 500. Can you see this is at minus 500? So that's what is expected now. We expected the 0 to be at origin, pole to be at minus 500. That's what is this. And what is the DC gain? DC gain is actually, this is 0 and 0 by anything is 0. So DC gain is 0. Just check the DC gain. DC gain is also 0. So this is my pole position, 0 position, this. Okay, this is the 4 or the 6 basic circuits what we looked into. Let us see one more circuit where we have a 7 circuit. I have something like this now. So let me name this as so this is C1 R1, this is R2 C2, this is V0, this is Vn. Of course, I have shared you the transfer function for all these things. So directly writing the transfer function of this and trying to locate the poles and zeros, this comes out to be 1 plus S R1 C1 1 plus S R2 C2 divided by S square R1 R2 C1 C2 plus S into R1 C1 plus C2 plus R2 C2 plus 1. So this is a transfer function what will result in. So from this we can clearly know that there are two finite zeros and there are two poles. Of course, where is the pole position, that purely depends on what the coefficients of this, which depends on the values of R1, R2. Now this is very clear that I'm going to have a 0 at minus 1 over R1 C1 and I'll have one more 0 at minus 1 over R2 C2. Now let me just keep this at minus 1000. Let me keep this at minus 10,000. So to keep this at minus 1000, so which is R1 C1, so let this be of course, if it is 1 micro and if it is 1 micro, to have this 0 at minus 1000 corresponding to this one, so this should be having a value 1 kilo ohm. So to have the second 0 at minus 10,000 with this as 1 microfarad, because you know that if this is 1 micro and if this has to be at minus 10,000, so the R2 has to be 100 ohm. And with this R1 as 1k and R2 as 100 ohm and C1 C2 as 1 micro, so you can substitute the values of R1 R2 over here and then actually find out what is the coefficients of this and the roots of it, so which will give me the pole position. So poles will be over here and here. Let us exactly know the pole positions. Maybe you can just use Calci to know the roots of it. I will do the MATLAB simulation. So where is my code here? Just have a look at the code. Maybe I have written it somewhere, so let me just try to open it and then maybe somewhere here it is. Okay, I don't think I have it here. So let me just edit that. So what is that seventh one I need to have? So this should be, let me have this entire thing copied. So this is fine, I can just put it here. So this is my 7th circuit. So along with this I should have R2 also, sorry C2 also. Let me just add that. So this is my C2 and this should be C, and the numerator, of course this happens to be, suppose if you want to get this, if you want to edit this transfer function, can I just write it like this? So what is the product of this? Shall I write it as S square R1 R2 C1 C2 plus, that's what is this, and then do you have it as S into R1 C1 plus R2 C2 plus 1. So that will be my numerator. Because fine. Okay, what I'll do, I'll go back to this. Sorry. Hey, come on. So this is my 7th circuit. So here it is. Let me write R2 into Okay, C2 is also there. That's what is the coefficient of, let me open the parenthesis. This is the coefficient of S square. What is the coefficient of S? It is R1 into C1 plus R2 into C2, and this is 1, and the quotient of this is, okay, let me just copy this again, Control C. This is the similar transfer function, but only in the denominator I have plus R1 C2 plus R1 into C2. This will have, and rest of thing is fine. Okay, now so this should end up with of course the DC gain of this should be 1. The DC gain of this should be 1. Should it be 1? This is infinity. This is okay, this should be 1. Let us find out. So we are expecting poles at zeros at -1000 and -10,000 for R1 R2 to be 1K and okay, let me just okay, now it is now R1 is 1K 1000, C1 is 1 micro 1 E minus 6, R2 is 100 ohm, this is again 1 E minus 6. You can see now I have, of course I am supposed to get a DC gain of 1. So before that, what is my pole position? Can you see the 0 position is at it's actually, see this is actually 10 power 4. This is my 0 position. Can you see it is, one is at -1000, this is -1000, this is actually -10,000. That's what is the expected 0 positions. So 0 positions are at pole is at, 0 is at -1000 and this is -10,000. Where is the poles? So poles are at 488, that is -488 and -2000. It's actually 10 power 4. Okay, it's at 20,000. It's at 20,512. So this is the pole positions. If you have a look at it, this is the pole position. This is at -488, whereas this is at -20,512. So this is my pole position. This is my another pole position. These two are the 0 positions. So DC gain, suppose if you substitute S as 0 here, if this is 0, that is 0, then this is 1, this is 0, this is 0, do you end up with 1 plus 0 by 0 plus 0 plus 1. So is it not 1? So this is my DC gain. DC gain is 1. That means this is open circuit, this is also open circuit. When these two are open circuit, so you have a resistor only, no current is flowing. So whatever is the input, same is the output. So DC gain is 1. So DC gain 1 means output follows the input. Output follows the input. Okay. In this video, we shall just recap all these different RC networks and their realization of poles and zeros, and what is the impact of adding a resistor in series with capacitor, in parallel with the capacitor, and we could able to see what is the pole and 0 position, how it moves, and what is the DC gain of the system. So maybe in coming videos we'll also see what is high frequency gain. So maybe high frequency gain, all those things are relevant when we actually do a frequency response of circuit. So that may be in the Bode plot of the control system. Thank you so much. Please simulate, do it for n number of different values of R and C, and have a hold on the circuits. Thank you.